This fourth video on astrophysics shows how a single diagram that plots the luminosity versus the surface temperature of stars reveals patterns that help understand the inner workings of stars. This diagram is called the Hertzsprung-Russell diagram. As always on this channel, you can expect a clear and concise explanation of each topic. Please don't forget to click on the like button, subscribe to our channel and activate the notification bell. Your support is crucial for our channel's growth and enables us to continue creating quality content. Thank you in advance for your support. In the early 20th century, two scientists, Hertzsprung and Russell, separately plotted similar diagrams of luminosity versus temperature in order to determine whether or not there was any pattern in the way stars were distributed. In the diagram, the vertical axis represents luminosity in units of the sun's luminosity. The horizontal axis shows the star's surface temperature in Kelvin. The temperature decreases to the right. Each star is represented by a point on the diagram. If there were no similarities in the composition of different stars, they could have many different combinations of temperature, size, and luminosity. This would lead to them being randomly distributed on a luminosity temperature diagram. Astronomers have noticed that when the absolute magnitude of stars is plotted against their surface temperature, the stars are not randomly scattered across the graph, but are mainly restricted to a few well-defined regions. Thus, they concluded that there is a correlation between a star's luminosity and its surface temperature, and that stars in the same regions share a common set of characteristics. They are divided into four principal groupings. The main sequence. A main diagonal band that runs from the upper left corner to the lower right corner and contains most of the stars. This is where stars are stable and long-lived, and where nuclear fusion of hydrogen is the dominant energy-producing mechanism in the stars. The Sun is a main sequence star of average mass and luminosity, spectral class G, and its position is shown in figure. At the top left are stars of large luminosity and high surface temperature, and at the bottom right are stars of small luminosity and low surface temperature, reddish stars. Red giant stars. At the top right are red giant stars. Red giants are similar in mass to our Sun, but have an expanded outer shell and hence large size and surface area. For this reason, they are called giant stars. They have low surface temperatures and are therefore rather but highly luminous. Nuclear fusion of helium occurs in their cores. Supergiant stars. In the upper right corner, above the red giants, are supergiant stars. Supergiant stars are much brighter and larger than giant stars. Masses typically 10 to 100 times that of the Sun. In their cores, the temperatures are hot enough for nuclear fusion reactions to produce carbon and heavier elements. White dwarfs. These stars are found at the bottom left corner of the HR diagram. Although these stars have a very hot surface, they are relatively dull because they are so small. These stars are at the end of their lives. Nuclear fusion has stopped. The stars have collapsed and are now cooling down. They are extremely dense. In general, we can say that any stars located vertically above the main sequence must be larger than main sequence stars in order to have higher luminosity at the same temperature. By similar reasoning, any stars vertically below the main sequence must be smaller than main sequence stars of the same temperature. The relationship between luminosity and mass for main sequence stars is described by the following equation. This relation comes from application of the laws of nuclear physics to stars. Now we'll see with some examples how we can use the HR diagram to estimate some stellar quantities. From the HR diagram, we see that such a temperature corresponds to approximately the same luminosity as the Sun. That is, we now use the equation for apparent brightness. Its distance from us in parsecs is from Wien's law, we find the temperature of the star to be given by the luminosity estimated for a main sequence star on the HR diagram of 100 times that of the Sun. We now use the equation for apparent brightness. Its distance from us in parsecs is the luminosity of a star is proportional to the fourth power of the Kelvin temperature. We are given that they have the same absolute magnitude. So, from the HR diagram, we know that they have the same luminosity. Therefore, we can equate the luminosity of the red giant with the luminosity of the main sequence star. After cancelling similar terms on both sides of this equation and rearranging gives the ratio. The radius of the red giant is therefore 25 times the radius of the main sequence star. We know that a star has an absolute magnitude of 10. So from the HR diagram, we know that the luminosity is about 1/100th of the luminosity of the Sun, using the mass-luminosity relationship gives. Therefore, the mass of the Sun is 3.7 times the mass of the star. You may have already noticed that the HR diagram can be used to describe the evolution of stars because the stages of stellar evolution occupy specific regions on the HR diagram. But so that the video doesn't get too long, the evolution of the stars will be shown in the next video.